Thermal energy storage is achieved with greatly differing technologies that collectively accommodate a wide range of needs. It allows excess thermal energy to be collected for later use, hours, days or many months later, at individual building, multi-user building, district, town or even regional scale depending on the specific technology. As examples, energy demand can be balanced between daytime and nighttime. Summer heat from solar collectors can be stored interseasonally for use in winter, and cold obtained from winter air can be provided for summer air conditioning. Storage mediums include water or ice slush tanks ranging from small to massive, masses of native earth or bedrock accessed with heat exchangers in clusters of small diameter boreholes, deep aquifers contained between impermeable strata, shallow, lined pits filled with gravel and water and top insulated, and eutectic, phase change materials. Other sources of thermal energy for storage include heat or cold produced with heat pumps from off-peak, lower-cost electric power, a practice called peak shaving, heat from combined heat and power plants, heat produced by renewable electrical energy that exceeds grid demand, and waste heat from industrial processes. Heat storage, both seasonal and short-term, is considered an important means for cheaply balancing high shares of variable renewable electricity production and integration of electricity in heating sectors in energy systems almost or completely fed by renewable energy. Solar energy storage. Most practical active solar heating systems provide storage for from a few hours to a day's worth of energy collected. There are a growing number of facilities that use seasonal thermal energy storage, enabling solar energy to be stored in summer for space heating use during winter. The Drake Landing Solar Community in Alberta, Canada has now achieved a year-round 97% solar heating fraction, a world record and possible only by incorporating STES. Molten salt is a means of storing heat at a high temperature. This is a current commercial technology used in conjunction with concentrated solar power for later use in electricity generation, to allow solar power to provide electricity on a more continuous basis. These molten salts have the property to absorb and store the heat energy that is released to the water, to transfer energy when needed. To improve the salt properties, it must be mixed in a eutectic mixture. The use of both latent heat and sensible heat are also possible with high-temperature solar thermal input. Various eutectic mixtures of metals, such as aluminium and silicon, offer a high melting point suited to efficient steam generation, while high alumina cement-based materials offer good thermal storage capabilities. Economics. High peak loads drive the capital expenditures of the electricity generation industry. The industry meets these peak loads with low-efficiency peaking power plants, usually gas turbines, which have lower capital costs and, since the recent drop in natural gas prices, have low fuel costs as well. A kilowatt-hour of electricity consumed at night can be produced at much lower marginal cost. Utilities have begun to pass these lower costs to consumers, in the form of time-of-use rates, or real-time pricing rates. Heat storage in tanks or rock caverns. A steam accumulator consists of an insulated steel pressure tank containing hot water and steam under pressure. As a heat storage device, it is used to mediate heat production by a variable or steady source from a variable demand for heat. Steam accumulators may take on a significance for energy storage in solar thermal energy projects. Large stores are widely used in Scandinavia to store heat for several days, to decouple heat and power production and to help meet peak demands. Interseasonal storage in caverns has been investigated and appear to be economical. Heat storage in hot rocks, concrete, pebbles, etc. Water has one of the highest thermal capacities, heat capacity 4.2 J, whereas concrete has about one-third of that. On the other hand, concrete can be heated to much higher temperatures, 1200 degrees Celsius by e.g. electrical heating, and therefore has a much higher overall volumetric capacity. Thus, in the example below, an insulated cube of about 2.8 m would appear to provide sufficient storage for a single house to meet 50% of heating demand. This could, in principle, be used to store surplus wind or PV heat due to the ability of electrical heating to reach high temperatures. At the neighborhood level, the Wiggenhausen-Sud solar development at Friedrichshafen has received international attention. This features a 12,000 m3 reinforced concrete thermal store linked to 4,300 m² of solar collectors, which will supply the 570 houses with around 50% of their heating and hot water. 12 electric thermal storage heaters. These are commonplace in European homes and consist of high-density ceramic bricks heated to a high temperature with electricity, and well insulated to release heat over a number of hours. Ice-based technology. Air conditioning can be provided more economically by using cheaper electricity at night to freeze water into ice, then using the cool of the ice in the afternoon to reduce the electricity needed to handle air conditioning demands. Thermal energy storage using ice makes use of the large heat of fusion of water. 1 metric ton of water, 1 cubic meter, can store 334 million joules or 317,000 BTUs. In fact, ice was originally transported from mountains to cities for use as a coolant, and the original definition of a ton of cooling capacity was the heat to melt 1 ton of ice every 24 hours. This is the heat flow one would expect in a 3,000 square foot house in Boston in the summer. This definition has since been replaced by less archaic units. 1 ton HVAC capacity equals 12,000 BTU/hour. Either way, an agreeably small storage facility can hold enough ice to cool a large building for a day or a week. Whether that ice is produced by anhydrous ammonia chillers or hauled in by horse-drawn carts. As such, there are developing and developed applications where ice is produced during off-peak periods and used for cooling at later time. In addition to using ice in cooling applications, it is also being used in heat pump-based heating systems. In these applications, the phase change energy provides a very significant layer of thermal capacity that is near the bottom range of temperature that water source heat pumps can operate in. This allows the system to ride out the heaviest heating load conditions and extends the time frame by which the source energy elements can contribute heat back into the system. Cryogenic energy storage. This uses liquefaction of air or nitrogen as an energy store. A pilot cryogenic energy system that uses liquid air as the energy store, and low-grade waste heat to drive the thermal re-expansion of the air, has been operating at a power station in Slough, UK since 2010. Molten salt technology. Molten salt can be employed as a thermal energy storage method to retain thermal energy collected by a solar tower or solar trough of a concentrated solar power plant, so that it can be used to generate electricity in bad weather or at night. It was demonstrated in the Solar 2 project from 1995 to 1999. The system is predicted to have an annual efficiency of 99%, a reference to the energy retained by storing heat before turning it into electricity, versus converting heat directly into electricity. The molten salt mixtures vary. The most extended mixture contains sodium nitrate, potassium nitrate and calcium nitrate. It is non-flammable and non-toxic, and has already been used in the chemical and metals industries as a heat transport fluid. So experience with such systems exists in non-solar applications. The salt melts at 131 degrees Celsius. It is kept liquid at 288 degrees Celsius in an insulated, cold storage tank. The liquid salt is pumped through panels in a solar collector where the focused sun heats it to 566 degrees Celsius. It is then sent to a hot storage tank. This is so well insulated that the thermal energy can be usefully stored for up to a week. When electricity is needed, The hot salt is pumped to a conventional steam generator to produce superheated steam for a turbine generator as used in any conventional coal, oil or nuclear power plant. A 100 megawatt turbine would need a tank of about 9.1 meters tall and 24 meters in diameter to drive it for 4 hours by this design. Several parabolic trough power plants in Spain and solar power tower developer Solar Reserve use this thermal energy storage concept. The Solana generating station in the U.S. has 6 hours of storage by molten salt. Pumped heat electricity storage. In pumped heat electricity storage, a reversible heat pump system is used to store energy as a temperature difference between two heat stores. Isentropic One system currently being developed by the UK-based company Isentropic operates as follows. It comprises two insulated containers, a hot vessel storing thermal energy at high temperature and high pressure, and a cold vessel storing thermal energy at low temperature and low pressure. Both vessels are filled with crushed rock or gravel which acts as the heat storage medium. The vessels are connected at top and bottom by pipes and the whole system is filled with the inert gas argon. During the charging cycle, the system uses surplus electricity to work as a heat pump. Argon at ambient temperature and pressure from the top of the cold store is compressed adiabatically to a pressure of 12 bars, heating it to around 500 degrees Celsius. The compressed gas is transferred to the top of the hot vessel where it percolates down through the gravel, transferring its heat to the rock and cooling to ambient temperature. The cooled, but still pressurized, gas emerging at the bottom of the vessel is then expanded back down to 1 bar, which lowers its temperature to minus 150 degrees Celsius. The cold gas is then passed up through the cold vessel where it cools the rock while being warmed back to its initial condition. The energy is recovered as electricity by reversing the cycle. The hot gas from the hot vessel is expanded to drive a generator and then supplied to the cold store. The cooled gas retrieved from the bottom of the cold store is compressed, which heats the gas to ambient temperature. The gas is then transferred to the bottom of the hot vessel to be reheated. The compression and expansion processes are provided by a specially designed reciprocating machine using sliding valves. Surplus heat generated by inefficiencies in the process is shed to the environment through heat exchangers during the discharging cycle. The developer claims that a round-trip efficiency of 72 to 80% is achievable. This compares to greater than 80% achievable with pumped hydro energy storage. Other systems. Another proposed system uses turbo machinery and is capable of operating at much higher power levels. Research. Storing energy in molecular bonds is being investigated. Energy densities equivalent to lithium-ion batteries have been achieved.